Alright, physics, here we go again. We left off talking about... Oh, this looks like just a basic circuit symbol. Sorry. I'm trying to make sure that I keep your class and the AP class separate. So, left off talking about kind of basic circuit symbols. I don't think, doesn't look like I talked about, no, nothing about like the voltmeter, ammeter, right? So these two symbols here, the voltmeter and the ammeter, I'm going to talk about those really quickly. Then I'll explain about these last few equations. And we'll kind of work our way through reviewing and reading how to like answer and how to look at all the rest of these electricity questions. All right? So, let me... Oh, goodness. What the heck was that? There we go. Let me come back to my original, very simple circuit here. Right? And I'll copy it down again because I'm gonna do something with it. All right. What I'm gonna do is I'm gonna say I want to know how fast our charge is going through this circuit. I would like to know what is I. But I want to do it without necessarily knowing how big this resistor is. So the easiest way that I could do it is I could use, and I'll focus kind of like that. Yeah, that'll do. So what I could use is one of those symbols, which was a circle with an A in it. This was an ammeter. It measures current. Through, oh, I'm like crooked here. Measures current through a portion of a circuit. Yeah, there. Now I'm straightening out my text here. It has negligible resistance, and it connects in series, right? So if I wanted to measure how much current is going through this, how come you didn't make a circle for me there? What the heck? Whatever, close enough. So I would do that. And if I did that, that ammeter, this thing right here, would measure how much current is literally going through this section, right? It's negligible resistance, so it's not going to add any resistance. It's not going to slow charges down. It literally just kind of clocks them at times. How many charges go by in a second? That's what an ammeter does. It measures current, right? If I wanted to, again, take a similar circuit, trying to figure out if I'm hearing things or not. I don't, whatever, it's fine. Pretty sure I'm hearing things. It's okay. I take a similar... Man, now I overcorrected. Went too far the other way. That's okay. So let's say I want to know... oh. I actually... You know what? Let me fix it entirely. Let me try to make it... No, there's definitely a conversation happening. Okay. That's fine. Alright, so we have this slightly more complicated circuit. Let's say that I have R1, let's say that I have R2, and I want to know how much voltage is used to go, well, they would say how much voltage is used across R1, right? So how much voltage is used in this first resistor? How much energy does it take for charges to move through this thing, right? Eventually my thing will... There we go. So how much voltage is used across R1? Well, to measure that, I could use something called a voltmeter. Right, this is something that it measures voltage. Shocker. It has infinite resistance, basically. And we need to connect this in parallel. The reason we need to connect this in parallel is because it has infinite resistance. If you try to connect this in series and you try to force charges through it, those charges are just going to get stuck because the resistance through this is just too high, right? So if I wanted to specifically measure how much voltage is used across R1, well, I would connect wires to either side of that, and I would put a voltmeter here. And what it does is it takes a reading at this spot, and it takes a reading at this spot, and it measures what's the difference between those two things. How much energy did it have right before it went through this thing? How much energy does it have right after it went through this thing? And it calculates a voltage based on that. So in this way, you can measure how much voltage does it take to actually go through R1. Right? I just want you to be aware. Ammeter measures current through a circuit, negligible resistance, connects in series. So it has to, charges actually have to go through an ammeter. Charges are going to be measured across a voltmeter. All right? So there's basics of the ammeter and the voltmeter. Other than that, there are 3 equations left down here. I'll address them all independently. And then again, there will be some questions that go online out of the Regents / your little green book, depending on whichever you have. If you don't have a little green book, you're fully remote, you don't actually need one. It's just something that's available to you. Again, if anybody wants a little green book, let me know. I will leave it in the office so that you can pick it up eventually. The only nice thing that the little green book has is like explanations to the questions. You do have access to the internet, you have access to me, you can always ask, you can always look, but sometimes it's nice to have that immediate answer. All right? One of the last equations that we look at looks like this. Right. This is a very specific equation, and I'd like you to make a little note of this. Either I'd recommend making this note in your reference table, but you can make it wherever you happen to write stuff down. Right? This equation is specifically the resistance of a wire, right? And we will use this equation when you are dealing with a wire, right? This L is, that's not how you spell length. This L is length. This A is the area of the wire, and rho is something called my goodness. Resistivity. This resistivity is something unique to different materials, and sure enough, it is not something that you need to memorize, not something that you need to know off the top of your head. There we go. There is a list of resistivities here for different materials. You'll notice it's at 20 degrees Celsius. So very often, if you have to use this equation, you will be told that you have a wire of a certain material at 20 degrees Celsius. Very specific conditions call for very specific numbers, which is what we have here. Right? The thing to notice about this equation, a longer wire has more resistance. That should kind of make sense. It's more difficult to get through something this length than it would be to get through something this length, just because it's longer. Area matters because it would be more difficult to get through a wire that has this kind of area versus a wire that has this kind of area, right? This one is going to be more difficult to get through because less charges will fit in it, right? So that's why the area is in the denominator, and then the resistivity is purely dependent on what it's made out of. I do want to point one resistivity out because it can throw people off. It's the resistivity for nichrome. All the other resistivities are like single digit point something times 10 to the negative 8. Nichrome is 150. This is not 1.5, it's 150. So just watch out for that. Other than that, you will be tipped off very clearly when to use that equation, because you will be asked specifically about the resistance of a wire. Right? P, if you remember before, was for power. It's electrical power, so watts, right? What is the power output of a light bulb? It is V times I, right? I used to call this the Poison-Ivy equation because I learned it as P equals IV. But power equals V times I, it's voltage times current, right? There are other versions of the equation. The only thing that these versions of the equation do are substitute for V from this or substitute for I from this, right? Again, you will be prompted. Now, how much electrical power? All right, not mechanical power, because that was on the other page. This is electrical power. Alternatively, this is work. Whoa. Well, this equation right here is just power equals work divided by time. They just multiplied both sides by time. So work, or electrical energy, again, you will be prompted very specifically. Electrical energy is power times time. The only thing that they do here is a substitute for power. So VI is power, that's what they substitute here, and then they just continue to substitute. I squared R is also power. But you will be prompted very clearly. Electrical power, electrical energy, electrical work. Resistance in a wire, right? There are these very specific keywords in a question that will clue you in on, oh, I need to do exactly this, all right? This is what I meant when I said electricity is like nicer than the rest of it. One, most of it kind of follows logically, right? You can work your way through this. This is how stuff works. Second, pretty much always you will be prompted exactly, use this thing with electricity. Use this thing with electricity. Interpret this diagram using electricity, using the concepts that are on the electricity page, all right? That's why electricity is only, it has far fewer equations. You do have to do diagrams, but they're fairly straightforward. Right. Now again, there are going to be questions here. There is a lab that I'm going to do in the near future. Students who are hybrid, who are in class, will probably do something during class, but we might end up doing a simulation too. Fully remote students, you will definitely have a simulation. That will be posted a little later this week. It will be due by the end of the marking period, so like Friday, but I guess really, like, I can give you until Sunday. I'm not going to fuss too much over that. Make sure to look for those questions. They should be posted. By the time this video goes up, it'll probably be posted. And, yeah. That's what I got. Look, if you have questions, if things are still confusing, please email. Otherwise, I will see you in class. I'll see you in the next video. Until then, take care, y'all, kids.